Hi everyone. So today we're going to be presenting the Smart Work Chapter 11 Question 12. And the people who made this presentation are Drew Gaddy, Geraldine Puerto, and me, Sad. So our question is asking us to calculate the osmotic pressure of each of the following aqueous solutions at 27 degrees Celsius. And the first value that we're given is 0.247 molar glucose, and they want that answer in ATMs. And our second value that we're given is 0.00740 molar K2SO4. And again, they want that answer in ATM. And the first relevant terminology, rather, that will help us solve this equation is what are colligative properties. And colligative properties are basically qualities of the solution that are reliant on the concentration rather than the identity of the particles dissolved in the solvent. And so basically that doesn't mean that, let's say you have a solution of water, it doesn't matter whether you have glucose or any other element in that water. It's more about how much of that particular substances in the water itself. And then our second relevant term is dissociation, which is the process in which molecules split into smaller properties. So if that was water H2O, it would be H2 and oxygen, just basically, you know what that is. And then our third relevant term is the Van Hoff factor, which in the equation that you'll be seeing later is referred to as the letter I. And basically it refers to the number of particles. And it's actually, or more accurately to say, it's a ratio of concentration of solute particles in a given solution compared to this concentration of particles that would be there if the solute didn't dissociate, which is kind of tricky to think about. But basically, it tells us that what were the relevant changes that happen in the physical properties. And so on the side here, you see some of the basic colligative properties in this neat little chart that we have here. And it shows that one of them is the osmotic pressure, which is actually something we're going to be talking about in, I think, the next slide, and some other ones that we won't be discussing here, but you should know as they are. Colligative properties are the elevation of the boiling point, the lowering of the vapor pressure, and the depression of the freezing point. So the next relevant terminology that we'll be looking at is the first is the concentration gradient, and that's a measurement of how the concentration of a substance changes as it moves from one region to another. And related to that is the osmosis. And osmosis is the movement of water across a semi-permeable membrane from an area of high water concentration to an area of low water concentration, and the net flow is in one direction. And due to the movement in one direction, the side that used to be water deficient rises. And this is a concept that used to really trick me up. So basically, how I thought about it is that water in this is the solvent. So basically, the water wants to go from an area where there's a lot of water to an area that there's not a lot of water. And that's kind of shown in this little graphic that we have here, but I'm going to go cover that a little later. And so then we have the osmotic pressure, which is a result of osmosis, and it's the pressure required to stop the net movement to the water deficient side. So as you can see in this little graphic here, and the initial state A, you have the semi-permeable membrane in the middle and a lot of glucose on the right side, which forms a solution with the water, versus the left side, which is just pure water. And so you can see glucose is moving between the two, but there's a lot more glucose on the right side. So to balance that out, the water will move to the right to make sure that there's equal amounts of water and glucose in there, which causes the water on the right side to rise up because there's more water there. And when external pressure is applied, as shown in C, the two will balance out, which will eventually create an equilibrium. The next relevant concept in dairy And the question that we want to ask is to find the osmotic pressure of glucose and potassium sulfate. And so the question we have to ask ourselves is, how do these two compounds behave when they dissolve in water? So both are aqueous solutions. Well, that's relevant, but what's more relevant is whether they're ionic or non-ionic compounds. And basically, since glucose is a non-ionic compound, when it's mixed with water, the compound doesn't dissociate into ions. So that glucose isn't really breaking down at all. The potassium sulfate is an ionic compound, so therefore when it's mixed with water, the compound does dissociate into potassium and sulfate ions, which is shown right here in this graphic. As you can see that the K2SO4, the potassium sulfate, is mixed with water and it breaks down into 2K plus, which is again aqueous, and the sulfate ion, which is also aqueous. So, what is the role of the Van Hoff factor in determining osmotic pressure? So first, if we have to establish that I, which again represents our Van Hoff factor, will be the same or different in both solutes in the question. So because glucose, again, which we know, doesn't dissociate in water, because if we look back here, we know it's a non-ionic compound, the I value is equal to 1 because it's just one particle. Versus potassium sulfate, it does dissociate in water, so the I value is equal to 3. And you guys should remember this, that the osmotic pressure is considered a colligative property, which again, if you go back a few slides, we talked about that. And an increase or decrease in the Van Hoff factor, whether or not a solute dissociates in water, does affect the colligative properties such as osmotic pressure due to the increase or decrease of particles in the solution, which makes sense because we know that our colligative properties are dependent on the concentration of the ions in the solution. So we can actually, now that we have all our relevant terminology and we understand what the question is asking us, we can basically try and solve it. So basically, first, we have this equation right here, which is the osmotic pressure is equal to I mRT, which we know that our I is our Van Hoff factor. M is the molarity, which is the moles of solute over the volume of the solution. R is our constant in the solution, and it's represented right there in that value. And T is the temperature in Kelvin. Second, we look at what was actually given to us in the problem. So we know that both solutions are aqueous. We know that both of the solutions are at 27 degrees Celsius, which when you do your conversion, it equals to 300 degrees Kelvin. And so our first solution is glucose and it has a molarity of 0.247 molar. And then our second solution is K2SO4 potassium sulfate, and that has a molarity of 0.00740 molar. Third, we identify the Van Hoff factor for both solutions, which, again, if you go back a few slides, we pretty much already know. And so glucose has a Van Hoff factor of 1, then this is because glucose is a non-ionic compound. And potassium sulfate has a Van Hoff factor of 3. That's because potassium sulfate dissociates into 3 ions. So finally, once we have all these different values here together, we can basically plug and chug at this point. And so basically when you multiply your I value, which is 1, your M value, which is 0.247, your R value, which is 0.0121, and your T value, which is 300, multiply all those together, make sure you're solving for your units, and basically when you multiply all those together you get 6.08 ATM. And again, we can do that with our second problem, and again you have N, or the osmotic pressure equals I mRT, and once you multiply all those together, again just basically plugging and chugging, you get the final result of 0.547 ATM. And basically this is our results that we got, and we know that they're correct. So what did we learn from this question? We learned how the Van Hoff factor, temperature, and molarity affect the osmotic pressure, as well as how they're all related. As for the role of Van Hoff factor, we can see that the big difference in the osmotic pressure is between a non-ionic compound and the ionic compound. The osmotic pressure is much higher for glucose because it didn't dissociate into different ions, and its molarity was greater than the potassium sulfate. And basically, we just learned how the colligative properties actually work in an equation. And of course, we're going to ask whether our answer makes sense, and we found that yes, it does, because the osmotic pressure of glucose in the question is 6.08 atm, and the osmotic pressure of potassium sulfate is 0.547 atm. And we can remember that the temperature was the same for the both, and the only factors that are different in the scenarios were the Van Hoff factor and the molarity. Finally, we have our references here, and if you want some more further clarity about the question, you can take a look at these. I highly recommend Khan Academy. It's a free resource, and it's really good at further breaking down these concepts better than we probably could. And again, you should also take a look at your notes as well. And that's it.